Okay, so we have different types of concrete. Depends on the application that we are where we use the concrete or what we use the concrete for. And the most common, the most used for the normal structure is the Portland cement concrete or the normal concrete. And of course, we have different application for high-rise building concrete and for the high strength, high performance, etc. So we started with the high strength concrete. The high strength concrete, the definition, the simplest definition of high strength concrete is concrete has high compressive strength. So high strength concrete is related to its compressive strength. So the concrete that has high compressive strength, we can call it high strength concrete. And the specific point that can differentiate between the normal and high strength concrete in terms of compressive strength, it was it kept changing over time. Initially, in 1950s, an example, the concrete has a compressive strength of 34 megapascal. Any concrete has a compressive strength of 34 megapascal and higher, we can call it high strength concrete. And below the concrete has compressive strength below 34 megapascal, we call it normal concrete. So 34 megapascal was the points or the compressive strength that can differentiate between the normal and high strength concrete. But when the time moves, in 1960s, an example, the number of the compressive strength can differentiate between the normal and the high was increased to 41 and even 52 megapascal. So 34 megapascal at this time is no longer high compressive strength or high strength concrete. And when the time moves again, the point that can differentiate between the normal and the high in terms of compressive strength was also modified and also increased to up to 62. So 42 and even 52 megapascal of compressive strength is no longer high compressive strength. So what you need to know that when the time moves, the point that can differentiate the normal and high strength concrete kept changing. So what is the point or the compressive strength in order to know whether the concrete is normal or high strength concrete? It simply can be defined as concrete with a compressive strength that is greater than that covered by the current code and standard. And when you design concrete with a specific compressive strength, the current standard or codes, they give you a methods, they standardize a methods and calculation sheet, and you go through this method, these steps, step by step, in order to do your mix design. How much cement, how much aggregate, how much water you need to mix in which ratio in order to achieve your target compressive strength. If you want to design a concrete with 30 megapascal, you follow the steps, you go through the calculation according to the standard, and you will come out with the ratios between the concrete materials, cement, aggregate, and water, if there is any admixtures. And if you go through all of them, you can get the mix design for the specific compressive strength. But some standards they give you the limit, the maximum compressive strength that you can design using this standardized and this methods. So any compressive strength value that not be covered by the standard that beyond the maximum of the current standard, we can call it this is high strength concrete. So there is no specific method that produced by the standard or the code that give you simply this is the method. If you apply this method and you go through this calculation, you can design high strength concrete. There is no standard tells you, or there is no standard gives you this calculation, but they might give you a method or something that can help you in order to achieve high compressive strength. Example of the things that they can help you in achieving high strength. Okay, they can provide charts or general chart that if you want to design high strength concrete, the first step that you need to minimize, like reduce the water to cement ratio. So the reduction in the water contents in the concrete can significantly increase the compressive strength of the concrete. They can also provide information that can also help the selection of the aggregates in the concrete, and it's well known that the use of low maximum aggregate size, if we reduce the maximum aggregate size, it can also increase the compressive strength of concrete. And the higher maximum size of aggregate is the lower strength of concrete. It means like, you know that the coarse aggregate, it comes in range, and the minimum particle size of the coarse aggregate is 4.75 millimeters, and it can goes up to 22 millimeters, for 14, 19. So the range, the maximum size, the range between 4.75 up to 14 millimeter, or 4.75 up to 19 millimeters particle size in this range, or you can use 14.75 up to 22 millimeter coarse aggregates. So the range and the changing in the maximum size, it also can affect the strength of the concrete. And how it affects: the minimum maximum size is the higher compressive strength of concrete. If I give you two mixes and I'm giving you that they are using the same ratio, the same mix design, the same contents of the cement, the same contents of the aggregate, and the same contents of the water, and I'm giving you that the only the change between these two mixes, that this mix use okay, aggregate, the same contents of the aggregate also, but one of the mix use the maximum size of coarse aggregate up to 14 millimeters, in which the other mix gives you the maximum aggregate size of 20 millimeters. So we have mix one that use maximum size of 14 millimeters, and the other mix use 19 or 20 millimeter maximum size of the aggregate. They have used the same contents. Like if you're using 10 kilogram of aggregate in mix one, he also used 10 kilogram of aggregate in mix two. 5 kilogram of cement in mix one is the same as 5 kilogram of cement. The water contents from the first mix is the same. The only difference between both of them is the range of the aggregates that can be used in both mixes. The first one has lower maximum size, and mix two has maximum size of 19 or 20. So we have mix one and mix two. Which one do you think will give, if we compare both of them together, which one will give higher compressive strength? So I need to listen from you. So we have mix one and we have mix two. Again, we have mix one and mix two. Mix one and mix two have the same mix proportion, the same ratio, the same mix design. If I have cement contents from the first one is the same as the cement contents of the other one. Like if you use 5 kilograms of cement, mix 2 will use 5 kilograms of cement. Mix 1 will use 2 kilograms of water, mix 2 will use 2 kilograms of water. Mix 1 will use 10 kilograms of aggregate, the other one will use 10 kilograms of aggregate. The only difference here is the 10 kilograms of aggregates. For the first one, they use the size ranging between 4.75 up to 14 millimeter, the size. The second one, they use 10 kilograms of aggregate with the particle size ranging between 4.75 up to 20 or even 22 millimeter, but the same contents. Or the only change in the particle range, particle size range. So which one, if we compare it together, which one do you think might get higher compressive strength? Mix 1 or mix 2? I need to listen from you. Do you understand the question?
Yes, sir, we do.
So we have mix 1. I just mentioned initially that the higher maximum size is the lower strength of concrete. The higher range of particle size of aggregate gives lower compressive strength. Okay, if I have two mixes, again, if I have two mixes, different questions, I have two mixes and with the same mixed proportion, the same mix design, and I use water content from the first one, water to cement ratio is 0.3, and for the other one, I use water to cement ratio is 0.4. If we compare them together, which one will give higher compressive strength?
Sir, in the previous lecture, you have said, I think, that the large size of aggregate will make, it will be more better than the other.
In terms of the compressive strength?
Yeah.
The large particle or the maximum particle is the higher compressive strength of concrete. Do you think, is this what you mean?
Yeah, the mixed one.
Mix one that has lower minimum maximum size, or like if we have, let's say, just focus on the aggregate. I have two aggregates, the same contents in both mixes. And the first one, the aggregate size is ranging between 4.75 up to 14. The second one, 4.75 ranging up to 20. So this is mix 2 that has higher maximum size.
So the
So
second
mix
one,
1,
yes.
mix 2, which one give higher strength?
The second one, sir.
Why?
Because of size for the particles.
So you mean that the increase of particle size result in increase in the strength?
Yeah.
Okay, you, Martin, what do you think?
I think so.
So I'd like to maybe agree with him, but also, doesn't that mean that the higher part, the second one would have like more workability?
Okay, so you mean that the maximum size, the increase of the maximum size of particle will result in higher compressive strength?
Yeah.
Okay, but this is unfortunately it's not correct. The maximum size of aggregate reduce the compressive strength of concrete. Okay, you need to understand these kind of things. Why? As I said before, there is no specific calculation, there is no specific methods. If you go through all the standards, you cannot find methods, calculation method with the steps, helps you to design high compressive strength. But we have calculation, we have so many types of methods and steps that you go through it and can help you to design normal strength concrete. concrete up to 30, 40, 50 megapascal. It's okay, it's easy. But if you want to design concrete that has high compressive strength, and high compressive strength is, at these days, it might be defined as more than 80, more than 90, and even higher than 100 megapascal. So there is no standard, there is no method that you go step by step, and at the end of this sheet or at the end of this calculation, you can get to know how the mixed proportion, the mixed design, how much cement, how much aggregate, and how much water I can mix so I can get the high strength. There is no method like this one, but there is some information that can help you when you want to design this high strength concrete. This information helps you that you design. The first one is the water contents. The first or the most sensitive parameter or factor that can affect the strength of concrete is the water contents. So, or we can define it as water cement ratio. Do you have any idea how water cement ratio can affect the strength of concrete? Then we will move to the aggregate again, but we will start with the most important factor, water cement ratio or the water contents. How the water contents or water cement ratio can affect the strength of the concrete. Okay, in other words, the high water contents will increase or decrease the strength of concrete. The high water contents or the high water cement ratio will increase or decrease the strength.
I think decrease.
Decrease. You mean that the more water content is the lower strength?
Yes.
Yes, sir, because it will make segregation.
Okay, this is correct that it will decrease the strength, but not because only segregation. It has so many other factors. One of them is segregation. That the high water content, it's one of the factors that lead to segregation. But even if we don't have segregation but also have high water cement ratio, we still have lower strength. So the first factor and the most sensitive factor that affect the strength of concrete is water cement ratio. So you need to know how water cement ratio will affect the strength of the concrete. This is first. The second one is the aggregate size, particle aggregate size. You know, the aggregate come in different range, and the range of the coarse aggregate, as example, starts from 4.75 or 4 or 5, depends on the standard. So the minimum particle size of the coarse aggregate, let's say 4, and the maximum, it can go up to 14 millimeter, or it can go up to 19 millimeter, or it can goes up to 22 millimeter, the maximum size. So this is the other parameter that you need to look in order to that will help you in the mix design or achieve high strength concrete. So in order to design high strength concrete, which range you need to use? You need to increase the maximum size or decrease the maximum size, and how it will affect the strength of concrete. I just answered this one just now. You just need to repeat it. The maximum size, the high maximum size. I have two mixes again. I have two mixes. The first with the same mixed proportions, same mix design, same ratio for the material, but they only have different by the particle size of aggregates. The first mix has ranging between 4 up to 14 millimeters. The second mix use aggregate ranging between 4 up to 20 millimeters. Which one of them will give higher compressive strength if we compare them together? One from 4 to 14 or 4 to 19 or 20? Which one of them will give higher strength? Mix 1 or mix 2? Can you hear the question? Do you hear the question?
Yeah.
So the increase of the maximum size or decreasing the maximum size, how it will affect the strength of concrete if we use higher maximum size of aggregate or lower maximum size of aggregate? So again, the higher maximum size of aggregate will increase or decrease the strength? I just answered this one before. Again. Okay, see, so the maximum aggregate size of aggregate will decrease the strength. It's an opposite relationship. If we increase the maximum size of aggregate, it will decrease the strength of the concrete. And if we use smaller particles, it will increase the strength of the concrete. So if I give you two options of maximum size of aggregate and I ask you, in order to get higher compressive strength, which option do you want? Which one of them you will select, or which one of them you will use? The option that have higher maximum size of aggregate, or the option that has lower maximum size of aggregate?
Lower.
Lower. So the small particles always give higher strength of concrete. This is in general. Just apply this one at any concrete materials: sand, aggregate, coarse aggregate, stone, or even in the binders. If you want to use cement and you have another filler material like silica fume or all this one, the particle size, the smaller particle size is the higher strength, always. So if you want to design high strength concrete, you need to start with the water cement ratio by reducing the water cement ratio, because you know that the lower water content is the higher strength of concrete. This is the first step. Second step, you start looking at the aggregate particle size. The lower or the small particle size is the higher strength of concrete. And both these two factors, that as a result of using less amount of water and as a result of using small particle size, yes, it will help the strength of concrete, but it also decrease the workability of the concrete. Of course, if you reduce the water, the concrete is no longer workable. The concrete is will become dry, harsh, difficult to mix, difficult to transport, difficult to compact. Why? Because the concrete has less amount of water. We reduce the amount of water because we need to reduce the water cement ratio in order to achieve high strength of concrete. So as a result of decreasing the water contents, it will affect negatively the workability of concrete. The concrete is dry, stiff, harsh, difficult to transport, difficult to mix, difficult to handle, difficult to compact the concrete. So how to avoid or how to solve this problem? How to improve the workability at the same time we don't need to increase the water in the concrete. At this time, or at this or for this mixed design, we need to use chemical admixtures. This chemical admixture, we call it super plasticizer or water reducing admixtures. This chemical admixture is being used in the concrete in order to improve the workability of the concrete at the same time without changing the water contents in the concrete. So with the same water contents, low water contents, we can keep it. Yes, we have workability problem. We can solve the workability problem by adding super plasticizer, the chemical admixtures, so we can achieve the workability at the same time having low water to cement ratio. Okay. The effect, we already have taken the effect of the water cement ratio on the workability of concrete, that the higher workable the low water content is the low workable concrete, and the high water contents or the high water to cement ratio is the high workable concrete. Now, what is the effect of the aggregate particle size on the workability of concrete? If I again, the same example, I have two mixes. The first one use coarse aggregate ranging between 4 up to 14, and the second one ranging between 4 up to 20 millimeter particle size of aggregate. Which one will give higher strength? One or two?
The first one.
First
Yeah.
one.
From 4 to 14.
Yes.
Okay. Which of them will give high workability, or how both of them can affect the workability of the concrete?
It depends on the water content, so I think it's same for both.
I think it's the first one.
Okay, if I use the same water contents for both of them,
Yes.
mix one has water cement ratio is 0.4, the second one water cement ratio is 0.4.
Yeah.
I maintain the water contents. Then I need to observe the effect of the particle size itself on the workability. I have a higher maximum size, it can go up to 20, and higher lower maximum size can go up to 14. So the maximum size to 14, and I have maximum size of 20. Which of them will give higher or lower, or how would affect the workability of concrete? Only the particle size, the effect of the particle size.
The one with the lower particle size would have more workability.
You mean the use of small
Particles.
will increase the workability, right?
Yes.
Muhammad, what do you think?
Yes, sir. The mix one.
Okay, but unfortunately, the opposite things. Always, the use of a small particle, it will increase the strength, right? But it will decrease the workability. The small particle will make the concrete quite stiff, harsh, and difficult to handle. But if we use large particles, it will improve the workability of concrete. So you need to memorize this one, and you need to consider this one in the site when you design for any mixed design in the site or anywhere. So always the lower or the smaller particle size decrease. So small decrease the workability. The large particle size, the higher particles, the biggest stone range, it can go up to 14, 15, 16. The higher particle size is the higher workability. Okay, so this is the first one. This kind of question, like you are giving a scenario and you need to find the best answer, the best solution, like case study. I'm giving you these two or I give you a scenario that we have water to cement ratio, we have a mixed design, and we have seen that we need to maintain the water cement ratio of 0.4, for example, and the concrete, we have found that the concrete is a little bit dry, or the workability is low. And what is the best option, what is the best solution scenarios that you need to do in order to improve the workability without using super plasticizer? This kind of scenarios that you may face, case studies. So based on your understanding, I give you like scenario, we have a mixed design here and we don't need to change the water contents in the concrete. What I have water cement ratio is 0.4 and I have this cement contents, this is aggregate contents, and we don't have, and the concrete is less workable. The workability of the concrete is low. So how can you improve the workability of this concrete without using super plasticizer? We don't have in the site super plasticizer. How can you improve the workability of the concrete without using super plasticizer, without adding water?
By increasing the particle size?
Increasing the particle size of aggregate, yes. So we can increase the particle size of aggregate is one of the methods to improve the workability of concrete. Okay, so when the time moves now, you need to understand all the factors, how it affects the engineering properties of the concrete, how the water contents can affect the workability, and how the water contents affect the strength of concrete. How the particle size of aggregate or the particle size in general can affect the durability, can affect the workability, and how it can affect the strength of concrete. You need to understand this one. You need to memorize it or understand it better, because this will be the key solution for any case or any scenario that you may face in the site, and it can help you a lot. How it can help you, this one, in the site after you graduate and you're working with a company or anything. You know, the maximum size of aggregate, it looks for you quite strange, and not all the people know about this one. And you know, the super plasticizer, which is a chemical, and it's quite expensive, and the owner or the concrete owner or the supplier, he want to achieve higher strength concretes, and he need to reduce the water cement ratio. This is the first step, and he use super plasticizer in order to back improve the workability as a result of the low water contents. So if he just try to play with the particle size of the aggregate, like instead of using 14, he can use increase to 20, 22. So it will significantly reduce the amount of super plasticizer that he can use. So he can try to improve the workability from the particle size of aggregates, can play in this area, which doesn't cost him so much. He will use the same aggregate. The aggregate cost is the same, whether small or big. He just play with the particle size. So through this one, if you know that this information, that if I increase the particle size of aggregate, I can a little improve the workability of concrete, and the amount of super plasticizer can be reduced. So I will use less super plasticizer, so I can save a significant money, significant cost because of the production of this concrete. So he can save, because the most expensive among all this one is the chemical admixture, super plasticizer. They add it in a small dosage. And you can also save money by reducing the use of super plasticizer. And in the site, I believe, I'm sure that not all of them, they know the effect of the particle size on the workability and on the strength of concrete. So we already have mentioned this one. So the high strength concrete, the ingredients or the material that we use in the high strength concrete is simply the normal concrete material with cement, aggregate, and water, but we have an extra material, we call it admixtures. These admixtures, it can be either chemical admixtures or mineral admixtures. The chemical admixtures, we have thousands types of mineral admixtures in the market, and the most common one used for the high strength concrete is the super plasticizer. What is the purpose of using super plasticizer? In order to improve the workability of the concrete. And why here it is essential to use super plasticizer in the concrete? We cannot design a concrete, high strength concrete, without super plasticizer. But we can design normal concrete, normal strength concrete. It's easy to design normal strength concrete and achieve the good workability without super plasticizer. But in high strength concrete, it is difficult. It is impossible, almost impossible to design high strength concrete without super plasticizer. Why? Because in normal concrete, we use water cement ratio, like normal water cement ratio, which is acceptable and it can give the required workability. But the first step in order to design high strength concrete, the first step you need to start with is by reducing the water cement ratio. Decrease the water contents. And once you decrease the water contents, the concrete will start to be harsh, stiff, dry, difficult to handle, difficult to transport, difficult to compact. So we need to maintain the same water contents, or same water to cement ratio, but we need to improve the workability. So how to improve the workability with maintaining the same water contents? By using super plasticizer. So super plasticizer improve the workability without changing in the water contents. This is the most common and must be used in designing high strength concrete, super plasticizer. This is one of the chemical admixtures. So the chemical admixtures, we have thousands of chemical admixtures. It's not only super plasticizer, but super plasticizer here, which must be used in production of high strength concrete. The other chemical admixtures, they have other functions, the other purpose to be used in the concrete. But for improving the workability, super plasticizer is being used to improve the workability. So it would be difficult to produce high strength concrete without using chemical admixtures, as I said. The super plasticizer gives the concrete adequate quality, workability at low water to cement ratio, leading to concrete with a greater strength. The other admixtures, we call it mineral admixtures or supplementary cementitious material or pozzolanic material. So we have three names to the mineral admixtures. Some people, they call it mineral admixtures. Some people, they call it mineral admixtures. Some, they call it supplementary cementitious material or cementing material. Some people, they call it pozzolanic material. So we have three names to the same material. If you heard any of them, they are the same material. So what is mineral admixtures? Mineral admixtures is a material used in the concrete as a cement replacement. What this material? We have silica fume, fly ash, slag. This is an example of these type of mineral admixtures that can be used in order to improve the strength of concrete. So mineral admixtures is being used in the concrete as a cement replacement, is not addition to the concrete. It means that we need to replace the cement contents with a percentage and add these mineral admixtures instead. If I have, and the ranging, it can go up to 50%. It means that I can, if I need to use, for example, 10% of mineral admixtures, 10% of the total weight of the cement, the binder. So I take out 10% of the cement and I add mineral admixtures instead. So I can replace it by 10%. I take out 10%, I add it, I replace it with the mineral admixtures. 15%, I can take up to 15%, I replace 20%, 30%. So the percentage is ranging and it's different from one type and another. Like for example, fly ash can go up to 30% by replacing, can replace 10%, 15, 20, 30%, or 35%. Slag, the slag also can goes up to 40%, 50% of the replacement. In which the, for example, the silica fume, the maximum is 15 or 20%. I cannot replace the cement more than 20% of the silica fume. And yes, with the increase of the cement replacement will increase the strength of the concrete, but at some point it will start decreasing. It start difficult to if we have like the percentage level, and with the compressive strength and the percentage level, and we can see that the higher percentage level is the higher strength, but at some points it will negatively affect the percentage level of the concrete. So, and this one would be the maximum, or it would be the optimum replacement level. If I replace level from like 5% here, 5, 10, 15, 20, yes, the higher replacement level is the higher strength of concrete. But at some point here, more than 20 percentage, it will start decreasing, the compressive strength decreasing. So there is no point to increase more than this amount, or this is the optimum, let's say optimum replacement level. This will have this kind of chart for the use of the different, we have different chart for different mineral admixtures. So we have concluded that the use of mineral admixtures as a cement replacement, not addition. We don't do addition. In the chemical here, we add addition. We don't replace anything. It's just a small dosage. I just add it to the mix and it improves the workability. This is the mineral admixtures. The chemical admixtures, oh sorry, the mineral admixtures here, how to use it? We use it as a cement replacement. We take part of the cement higher by mass. So it's a cement replacement, not addition. We don't add extra mineral admixture. It's the extra material to the mix. We just replace the percentage. Okay, so how the use of these mineral admixtures. This is one of the methods to improve the strength of concrete, further improve the strength of concrete. We can use this material as a cement replacement. It can improve the strength of concrete. Okay, in normal concrete, what binder do we use? We use cement. We have only cement, aggregate, and water. And the high cement content is the higher strength of concrete. But this is up just for a limit. Like if I want to use, if I want to achieve 15 megapascal, I can put this specific amount of cement. And if I want to increase it, I just increase the cement content. I can achieve 20 megapascal. If I need more, I can also increase the cement. So the high cement content is the higher strength. But also at some point here, if you keep increasing the cement contents, at some point it will start to negatively affect the strength of concrete. And this optimum would be the maximum strength that can be achieved by normal concrete, which can be like, for example, 40 megapascal or whatever, 35 megapascal. So I have a limit. I cannot achieve more strength. Even if I want to use so much cement, we still have a limit. So this is actually is the same as the point that differentiate between the normal and the high strength concrete. Up to here, the amount of cement that I can use here would be like standardized according to the steps calculation, and I can get the up to here. But so this is, for example, 40 megapascal. I need 40, I need 45, 50, 60 megapascal. How can I improve it? I cannot simply add more cement, because at some point the addition of cement is no longer effective on the strength of concrete or strength development of concrete. So how can I keep increasing or keep achieving the higher strength than the total or the limit of the cement cement contents? So one of the methods is by reducing water cement ratio. Another method is here using mineral admixtures. What is this mineral admixtures? This mineral admixture can be used as a cement replacement, and when I start using it as a cement replacement, I can achieve higher strength. The strength of the concrete will keep increasing. See, at some point, depends on the mix design. Okay. Again, what's special in this material that can increase the strength of the concrete furthermore by replacing it with the cement? So by using this one, I can increase furthermore the strength. So it helps in the achieving higher strength concrete, higher than the limit. Okay, or before this one, I need to define what is this material. This material is a waste material or byproduct materials as a result of different factories, and it's a waste material from different factories or different industry. So they collect it, they sieve it, and they start to use it in the cement. Okay, so what's special in this material? Why especially this material, which is waste material and byproduct material? The specialist in this material that it contains high amount of silica. It contains high amount of silica. It contains high amount of silica, CiO2. So any materials come in a powder form, whether byproduct or waste material from the industry, and it contains a high amount of silica, it can be, we can consider this material as mineral admixtures. So we can use this material as a cement replacement, partially cement replacement, in order to achieve higher and higher strength. Again, so why especially silica that can improve the strength of concrete? First is what is the source of the strength of concrete. The source of the strength of concrete is the calcium silica hydrate as an outcome from the cement hydration. So the cement hydration, when cement react with water, let's write it here. When the cement react with water, I have cement plus water, it gives us calcium silica hydrate plus calcium hydroxide. So this is the hydration of the cement. When cement get in touch with water, it can produce calcium silica hydrate gel and calcium hydroxide. Calcium silica hydrate, this is the source of the strength. This is what makes the concrete harden. This is the source of the strength of concrete. It means the higher calcium silica hydrate, the higher contents of calcium silica hydrate is the higher strength of concrete. So the more calcium silica hydrate in the concrete is the higher strength of concrete, and the lower calcium silica contents is the lower strength of concrete. So in order to achieve higher strength of concrete, we need to increase the calcium silica hydrate in the concrete. As a result of this reaction, 75% of the outcome of the reaction is calcium silica hydrate, and we have 25% calcium hydroxide. So this is the source of the strength that we need to focus on, and this is just an outcome from this reaction. I have 25%. I have 25%. So I have here 75% of the outcome is calcium silica hydrate, and also the other 25% is calcium hydroxide. So this is the source of the strength that occupies 75%. This is good value, but still I have 25% volume inside the concrete, calcium hydroxide, and this one has no benefit to the concrete. The concrete doesn't benefit anything from the calcium hydroxide inside the concrete. So I have 25% material or contents or products inside the concrete. 25% of the concrete volume is calcium hydroxide that has no benefit to the concrete. So when I use the mineral admixtures that contains a significant or high amount of silica, this silica will start to react with the calcium hydroxide that has no benefit to the concrete. So this is calcium hydroxide plus silica, and it will give us calcium hydrate extra. Okay, so we have this hydration. This is as a result of only the cement. When cement react with water, give us calcium silica hydrate 75%. The calcium silica hydrate is the source of the strength, and the higher calcium silica hydrate contents is the higher strength of concrete. And also as a result of this reaction, I have calcium hydroxide. 25% of the outcome is calcium hydroxide. Calcium hydroxide has no benefit to the concrete. So it's occupied a large volume inside the concrete, which is 25. So I have 25 products inside the concrete that has no benefit. It doesn't contribute to the strength, and it's even contribute to the decrease the strength of concrete, and later it will makes the concrete, helps the concrete to deteriorate, or it contribute to the failure of the concrete. There will be as a reason of the concrete failure. So in order to improve the strength furthermore, we add these mineral admixtures. These mineral admixtures that has high amount of silica. So the silica in the mineral admixtures, we start to react with this one that has no benefit to the concrete and produce calcium silica hydrate, the same as this one, extra. So I have extra calcium silica hydrate. I have 75, and I have also consumed this one and converted to calcium silica hydrate. And calcium silica hydrate is the source of the strength. The higher calcium silica hydrate is the higher strength of concrete. So what I did actually, I increased the calcium silica hydrate. With the increase in the calcium silica hydrate, the strength also increased. So I increased the strength of concrete further more. Here, this is the 75% of calcium silica hydrate, and I add mineral mixtures and they convert the calcium hydroxide to more calcium silica hydrate, so it's increased the strength furthermore. So one of the methods to produce or design high strength concrete, the first one is by reducing water cement ratio, and in order to achieve the good workability we use super plasticizer. Also one of the methods here by using mineral admixtures. This mineral admixtures, it can help in further increase the strength of concrete, and it has another way of contribution to the strength, which is the particle size. How the mineral admixtures, let's say the silica fume, if we select silica fume, how the silica fume, this type of mineral admixtures, can contribute to the strength of concrete. The first contribution is come from the chemical reaction, this one. So silica fume that contains 90% of the silica fume are silica, and the silica and the silica fume will react with calcium hydroxide and convert it to extra calcium silica hydrate, so it will increase the strength. It also another way of contribution to the strength by its particle size. The particle size of the silica fume is 100 times smaller than the cement particle size. So I have a particle size of cement, and the silica fume, the particle size is 100 times smaller. It's 100 times smaller than this, the particle size of the cement itself. So how do I get benefit of this one? The small particle size of the silica fume, the smaller particle size of this silica fume, will start to go and fill all the spaces, the small spaces between the particle size of the cement. How does it work? Like this. Or increasing the packing. If I have This cement particle size, an example. I have another one. Particle size here, particle size here, another particle size. This is the particle size of the cement as example. If I use material that has a particle size which is 100 times smaller than this one, which would be probably looks something like this one if we compare it. So these particle size will come and go and fill all the spaces between the particle size of the cement itself. So with the concrete or the general compacted of the concrete will be more compacted, more dense, and come and fill all the spaces between the particles. So the particles or the dense or the concrete will be more dense with less voids. So this is another method or another contribution comes from the silica fume in addition to this contribution, chemical contribution, and we have also the particle size contribution. We start to fill all the spaces between the particles. It will also make the concrete more compacted and will increase the strength of concrete. Okay, so we'll go for a break and we'll come back to continue for this one. So we'll come back at 11:30.
Okay, sir.
Let's write it here. Break until 11. Improve the strength of concrete by the chemical perspective and from the filling effect from the particle size also, and also the water contents and the use of super plasticizer, how it affects the strength of concrete. So in order to start, as I said before, the strength of concrete, high strength of concrete, there is no standardized, there is no methods, there is no steps that you can follow in order to achieve the high strength or design high strength concrete. But they can give you some information or some things, that criteria or factors that can help you in design, mixed design of concrete to achieve high strength concrete. The first one, we need to make sure the strength or the workability or the water content is low. We need to decrease or lower the water cement ratio. We need to use pozzolanic material or mineral admixtures or supplementary cementitious material, the same. There are three names with the same material. Why we need, what is the purpose of using pozzolanic material like silica fume? It's to prevent the formation of the calcium hydroxide. It's to prevent the formation of the calcium hydroxide. And then in the cement, which might reduce the strength at the cement aggregate bond. Silica fume has been shown to be particularly used in this application. It became the most common admixtures compressive strength that can be achieved higher than 80 megapascal. So among different material, mineral admixtures material, silica fume is the most effective one, and it can significantly improve the strength of concrete. Different materials has different effect on the strength of concrete. All of them can contribute to the strength, right? But the effect is different from one to another. And the most one that can significantly improve the strength of concrete is the silica fume. The aggregate must be selected carefully for high strength mixes, as weaker aggregate might not be strong enough to resist the load imposed on the aggregate. And here this is also the maximum size of coarse aggregate. And high strength concrete is normally below than 22 and down to 10 millimeters. So we need to, as we discussed before, we need to reduce the maximum size of the aggregate in order to achieve higher strength of concrete. We already have seen this one, the advantages of using high strength concrete and the parameters inside the concrete that reflect the strength. We have three main things that affect the strength of the concrete itself that we need to consider when we design for high strength concrete. We have the cement paste. Let's draw it something. If we have this, for example, this is the concretes. Inside the concrete, what do we have? We have aggregates, right? We have coarse aggregates distributed inside the concrete as filler material. Okay, and also we have sand. So aggregate can be either coarse or fine aggregate, the big stone, gravel, or the sand. Now, what are the properties that you need to discuss here, or you need to make sure that you understand it in order to design or understand the properties of the concrete in terms of its compressive strength? Now, the compressive strength of concrete is related to its compressive strength. High strength of concrete is related to its compressive strength of concrete. That must be high. How to determine the compressive strength of concrete? We put the concrete, we prepare a sample, cube or cylinder of concrete, we put it inside the machine, and we start to apply load. We start to apply the axial load to the concrete. We start to apply an axial load to the concrete. In the machine. Then the concrete will start, then we apply the load. Then we start to increase the load gradually until the concrete specimens or concrete sample fail or break. Then we take the maximum load, we divide it by this cross-section area, then we can calculate the compressive strength of the concrete. So this is the cube of concrete, putting in the machine, compression machine, then we start an axial load, and the load is increasing with time until the concrete specimen fail, and we take the maximum load at the time of failure divided by the cross-section area of the specimen. Then we can get the compressive strength of concrete. Now, the failure of the concrete, how the concrete fail? The concrete fail because as a result of three scenarios. The first one, okay, we have aggregates, we have cement paste, and we have aggregate to the cement paste bond, the bond between the aggregate and the cement paste. So these are aggregates surrounded here with the cement paste. So we have aggregate cement paste, and we have also aggregate to the cement paste bond. There is a bond here. How the aggregate bonded with the cement paste? Do they have like good bond? Are the good bond between the cement paste and the aggregate, or they have weak bonds between the aggregate and the cement base. So these are also properties that you need to examine or you need to look at, very important for the general compressive strength of concrete. So the strength of the concrete fail as a result of the fail of one of three things. If the aggregate itself, the particle aggregate itself, it's weak, then the failure will go through the weakness point. The crack of the failure of the concrete failure will go through the weakness point in the aggregate. So we have three scenarios. The aggregate or the concrete can be failed as a result of the aggregate itself, which is weak. So the crack will go through the particle and the whole concrete will fail. Or the concrete will fail because of the cement base itself. The cement base is weak, so the crack will go through the cement base. So the crack will find the way with which has the weakness part in the concrete. The weakness part of the concrete, it can be either the cement based or the aggregate itself, or the aggregate and the cement based bond, the bond between the aggregate and the cement base. So we have three parts inside the concrete can or affect the strength of concrete. If we have the concrete, the load will start applying on the concrete in general, and the crack will go through the weakness part, and the failure of any part will result to the failure of the whole concrete. Like if we cannot use good aggregate, very strong aggregate, at the same time we use weak paste. So whatever the aggregate is strong, how strong is the aggregate, the concrete will fail through the weakness point, which is the cement paste. And also at the same time, we cannot improve the cement paste, try to increase the strength of the cement paste, and we use weak aggregate. So the concrete will fail through the aggregate itself, and it will result to the whole concrete failure, no matter how strong it is the cement paste. Maybe the cement paste is very strong, but the aggregate is very weak. So the crack will go through the weakness point, which is the aggregate, and result to the whole concrete failure. Then there is no point to increase this cement paste. Also, we might have strong aggregates, we might have strong cement paste, but the bond between the aggregate and the cement paste is weak. So again, the crack will go through this one, will go around the weakness point here, the bond, and will fail. It will result to the concrete failure in general. So we have three properties that reflect the strength of concrete, or you need to look on the factors or the parameters or the properties of each of them, and you need to make sure that you achieve higher cement base strength, higher aggregate strength, and also higher bond between the aggregate and the cement base. You cannot just focus on one of them and leave the others. If you try to just improve the cement base and you achieve a concrete that has high cement base strength, but we have a weakness part here. So the concrete will, the load or the failure, it will not go and struggle to fail or break the strong base here. It will go to the easiest part. The weakness part here is the aggregate, so the crack will go through the aggregates. No matter how strong is the cement base, I already find the easiest way or the weakness part in the concrete. So the failure is always go through to find the weakness part in the concrete in general. And the concrete in general, we have three main parts that you need, that the cracks or the failure go through it. So the failure, it can move through the cement paste. This is one type of failure that the crack have seen, or the failure of the concrete of the load have seen that the weakness part here is the cement paste. So the failure, or when you put this one in the machine and it's failed, and you take it out and split it into two parts, and you can see where is the crack. The crack can went through it. So you can see that the particle, the aggregate particles, is still not broken, and the crack just went through the particle, through the cement paste, which is in this type of concrete was the weakness part. The other scenario, the other scenario is that the failure, it go through the aggregate and split it into, and can split it into two pieces, can break the aggregate, and the aggregate is weaker than the cement paste, and the aggregate was weaker, so it's easy to break the aggregate and go through it and make the concrete failure. This is the other scenario. The third scenario is the crack can go through this way, the bond between the aggregate and the cement paste. So we have three scenarios of failure. The first one is through the cement paste here, through the cement paste. The other one is through the aggregates, and the third one is through the bond between the aggregate and the cement paste. They have seen that they have good cement properties, they have strong aggregate, but the bond between the aggregate and the cement paste is weak, so the crack will go to this weakness point. Or the cement paste was weak, so the crack can go through the cement paste. Or the aggregate itself is weak, so the crack will go through the aggregate, which is the weakness point. So the first one, what are the factors, what are the properties that I need to consider for each of them? Starting with the cement paste, this part. What are the factors, or how to improve the cement paste properties that to try to improve it and avoid any failure that can be caused as a result of the cement paste? In conventional concrete technology, the strength of the paste is a function of its water to cement ratio, hydration reaction, water cement ratio. So the lower cement or the lower water contents is the higher strength of concrete, and the more compacted concretes and the higher strength. Water to cement ratio, we started before that one of the main parameters when you design the high strength concrete is the water contents and the water to cement ratio. This is only for the cement paste, when cement get in touch with water. And the water to cement ratio, it has nothing to do with the aggregates particle. It's nothing related to the sand or related to the strength of the aggregates. It's only related to the strength of the cement paste. The cement paste, or the hydration, is a function of time, and the development is increasing with time. This is because hydration of the cement with water. Aggregate sand is not part of any reaction happen for the strength development. The strength of the aggregate is the same. It doesn't improve over time. Aggregate is aggregate. If you the cement paste today, if you cast today the cement paste, the strength of the cement paste increasing over time, and the maximum strength reach at 28 days. But aggregate, the strength of the aggregate today, and you leave it for 1 month, 2 months, the strength of the aggregate is the same. It doesn't increase over time inside the concrete or outside the concrete. So the strength of the aggregate has nothing to do with the development of the strength. The strength of the aggregate is the same over time, doesn't change. So if we are looking only on the cement paste, we need to look at the water cement ratio, reducing water cement ratio. And the reduction in the water cement ratio will produce paste in which the cementitious particles are initially closer and more compacted and settled. This one, water cement ratio, is higher than the water cement ratio here. And the cement paste here, because the water cement ratio is higher, you can see that there is so much voids inside. And the more voids is the lower strength of concrete, in which if we decrease the water cement ratio, we can make the concrete more compacted. This is as a result of the cement or water contents. Another thing, we can use also mineral admixtures. Again, mineral admixtures, this one, the mineral admixtures, the benefit of the mineral admixtures is part of the cement. It has nothing to do with the aggregate. Aggregate is aggregate, sand is sand. The mineral admixtures, the water cement ratio, the reaction is all are part of the cement paste, the cement hydration. So the first one is the water cement ratio. It makes the concrete more compacted and it increases the strength, reduce the permeability, reduce the porous of the concrete paste. Also, the use of mineral admixtures can also further improve this reaction, which is part of the cement paste. Again, it's only for the cement paste. There is no reaction as a part of this of the aggregate. Aggregate is aggregate, sand is sand. Nothing to do with them in relation with the hydration. So also the other benefit is using the mineral admixtures that can improve the strength by the reaction, by consuming the calcium hydroxide, and also by filling these voids. It can be filled with this very fine and very small particles of silica fume or fly ash or any mineral admixture that has particle size smaller than the particle size of the cement. So these voids can also be filled by the mineral admixtures. So these are the methods to produce or to enhance the cement paste by reducing water cement ratio, reduce the porosity of the concrete, and also by filling all these voids inside the cement paste and make the concrete more compacted, cement more compacted. So also the same as the porosity can also be reduced by optimizing the particle size distribution from the cementitious material. Cementitious material is the mineral admixtures is the same by increasing the potential of packing density. This one is the same as by filling all this one, and this is what we call it packing. Increase packing, make it more compacted, and the distribution, particle size distribution. The second parameters is the aggregate and the cement paste bond, the bond. So this is also a factor that you need to look in order to guarantee has a good bond between both of them in order to avoid any crack or any failure can come through this one. So the transition zone properties is what is transition zone is the bond between the aggregate and the cement matrix or the cement paste. The bond here between how they are bonded together, do they have a good glue? Are they glued, well glued together, have a good bond or not? So the bond between the aggregate and the cement paste affect the general strength of concrete. And you can see here the transition zone between the stone and the paste here is very compacted, and it has a good bond between both of them. So how to increase the bond between both of them? You can use stone that has sharp broken edges, the stone that has rough surface, not rounded smooth surface. We need to have it rough surface and sharp broken edges. And also we need to minimize the water to cement ratio that makes this area is more compacted and filled with the cement paste. When fraction surface of filled conventional concrete are examined, it's often observed that the failure has occurred either with the paste, the failure having either from the paste, like this one, the failure has either from the paste or paste itself, or at the interface between the paste and the coarse aggregate particle, or within the particle itself. We already discussed this one. So normally when you do this, when you have the opportunity to do this one in the lab, try after the particle fail, you take it out, you split it into two parts using your hand, and you look where is the failure, the cracks, or from which part the crack happened. If you can see that the particles, aggregate particles, it's not broken, and the failure is went through the particles and reached to the other parts, it means that the failure as a result of, or the weakness points in this mix was this transition zone between the aggregate and the paste itself. So the bond between both of them was weak, and the cracks found its way through the weakness part, which was the aggregates to cement to the cement bond. And this kind of things that you can see that the bond between the aggregates, quartz, which is gravel or whatever, with the cement base, there is weak bond between both of them. So it will be definitely the weakness point with the concrete. Here you can see there is compacted, no voids with the particles, which is A is the gravel particles or the coarse aggregate particles. With the cement paste here, there is a good bond between both of them, and the good bond is the avoid the failure to come through it. So in total, we need to make sure, after we understand the failure scenarios, 3 failure scenarios, we need to take care of all of them. You don't just take care of 2 and leave the 3rd, because no matter how much you improve the cement paste, or no matter how much you improve the bond, if you are using a weak particles, the aggregate particle itself, it's weak, so the failure will easily go through the particle itself and the whole concrete will fail. So the concrete will fail as long as one of the 3 scenarios here, or 3 parts, fail. The weakness one will be the reason of the failure of the total concrete. High performance concrete, it's a concrete that related to the durability of concrete and the surface life of concrete. rather than the compressive strength of concrete. So high strength concrete is defined as a concrete that has high compressive strength at a given age. High performance concrete, no, it is a concrete that has high workable and high durable concrete, no matter how strong is the concrete. High performance concrete is a concrete that has high durable performance, high durability, not high strength concrete. And you will get to know that all the high strength concrete is high performance concrete, but not all the high performance concrete is high strength concrete. Like if you design a concrete that has high compressive strength, so it will by default is the same as it will be high performance concrete. So high strength concrete, all high strength concrete are high performance concrete, but not all the high performance concrete is high strength concrete. So you need also to understand this one. Again, all the high strength concrete are durable concrete or high performance concrete or concrete that has high durability. But not all the durable concrete has a high compressive strength. So high performance concrete is concrete that has achieved good durability properties to the concretes and can stay the surface life is higher than the normal concrete. And we have characteristics of the high performance concrete that all of them are related to its durability, that it can resist the chemical attacks, it can stay for high surface area, high surface life, high durable, it can resist the chemical attacks with a sulfate attack, acid attack, abrasion resistance, low permeable concretes. It can prevent or block any attack or any water to go and penetrate inside the concrete and avoid this water to reach to the steel bars. Because if the water could penetrate, and if the concrete has high permeable concrete, it means the water can easily go through the concrete, so it can easily reach to the steel bars. Then corrosion will start. The concrete in general start to deteriorate, and it will result at the end of the day to the structural failure. No volumetric change in this concrete. And you need to know that the concrete is always tend to shrink over time. The concrete doesn't expand. The volume of the concrete doesn't expand. The volume doesn't increase. The volume of the concrete is always looking to shrink rather than to expand. And that's why shrinkage is one of the problems that happen to the concrete. That the volumetric change in the concrete, the volume of the concrete reduced over time, doesn't expand. So this are the general characteristics of the high performance concrete that focus on the durability more rather than the strength of the concrete itself. We have another type of concrete, which is self-compacting concrete. Self-compacting concrete is a concrete that has high flowability and it can easily reach to all the spaces, and it doesn't require any mechanical vibration in order to allow the concrete to fill all the spaces or to remove all the bubbles. So self-compacting concrete, that concrete that it's compacted by itself from its name. So the concrete can compact it by itself and a high flowability, and it can reach to all the spaces by itself. And when do we need to use this kind of concrete? When we have like high dense of steel bars and it's very difficult to reach to some points inside the structures, and it will be difficult to compact some spaces here. So what they need to do, they need to use self-compacting concrete that can go and fill all the spaces by itself, and this is the characteristics of this kind of concrete. So how to achieve a high workable concrete or self-compacting concrete? By increasing the workability of the concrete. The high workable of concrete, it is the main things that we do to achieve self-compacting concrete, and by using super plasticizer. Okay, but it's not just simply we add super plasticizer, because the high, if we in normal concrete, in normal concrete or Portland cement concrete, if we just simply use high amount of super plasticizer, it will result to some problem like segregation or bleeding. So it is not just simply add more super plasticizer or more chemical in order to get high workable concrete. We need to consider other factors, like by increasing the fine particles inside the aggregate, whether the cement or by adding mineral admixtures, increase the binder contents. We need to just increase the binder contents together with adding the super plasticizer. So super plasticizer alone, it doesn't work with this kind of concrete, because the higher super plasticizer with normal concrete, it will result to segregation and a problem happen to the concrete. But in order to avoid segregation and bleeding happen as a result of the high amount of super plasticizer, we increase the amount of fine particles by increasing the cement contents, or by adding extra, increasing the volume of the or the weight of the fly ash or any other mineral admixtures. Another type of concrete is the lightweight concrete. The lightweight concrete simply can be defined as the concrete that has low density. And how much is the density? To differentiate between what is the number, the density, the number that can differentiate between the normal and high, or normal and lightweight concrete, depends actually on the standards. And the ACI standard define that the normal, the strength, oh sorry, the lightweight, the density of the lightweight concrete must be lower than 1,850 kilogram per cubic meter. That the density of the concrete has a density lower than this number or this value, we can call it lightweight concrete. And the density has concrete has a density higher than this value, then we can consider as normal weight concretes. And also, in order to use this kind of concrete, lightweight concrete, in the structural purpose, it must be the minimum according to the standard, the compressive strength not lower than 17 megapascal, the strength of this one. And as a result of decreasing the weight of the concrete, what are the methods that we follow in order to decrease the weight of the concrete? By creating voids inside the concrete itself. And the more voids inside the concrete is, yes, will be the lighter concrete, the low density concrete, but at the same time with the lower strength. So the lower density, lower strength, high density or heavy weight is the higher strength of concrete. And that's why we must make sure that we need to achieve a minimum of 17 megapascal for the concrete in order to be used as in the structural purpose. So what are the methods to produce lightweight concrete? We have 3 methods. The first one is by using lightweight aggregate. Since you know that the aggregate occupy around 75% inside the concrete. So 75% inside the concrete volume of the concrete are coming from the aggregate itself. So any significant or any change in the aggregate will have a significant change in the total concrete, because majority of the concrete is coming from the aggregates, the gravel or the sand, or any small change in the aggregates will make a significant change in the total concrete, whether for the strength, for the weight, or for anything. So we need to make sure that we need to use a good properties of the aggregate. So 75% of the weight of the total concrete, 75% coming from the aggregates. So if I have, for example, one sample of, let's take example of 1 kilogram of concrete, 1 kilogram of concrete. So let's say 750 grams are the weight of the aggregate itself, and 25 grams coming from the sand and from the cement and the water. So majority of the weight of the concrete coming as a result of the aggregate itself, 75%. And since the aggregate, the weight of the concrete, 75% of the weight of the concrete coming from the aggregate. So if we use lightweight aggregates, so we can significantly reduce the total weight of the concrete. So one of the first methods to produce lightweight concrete by using lightweight aggregates. Lightweight aggregate. The second one by, let's see here, it's related to also the aggregate, by not using fine aggregates. Not using fine aggregate. In other words, we don't use sand in the concrete. We only use cement, water, and coarse aggregate, gravel. We don't use sand. So this is also one of the methods to reduce the weight of the total concrete. The third one is related to the cement base, or we call it cellular concrete, by creating voids inside the cement base itself. With creating the voids in the cement base, it means we reduce also the total concrete weight. But the most one that significantly make change in the weight of concrete is by using lightweight aggregate, because aggregate, we have 75% of the total concrete weight, it's coming from the weight of the aggregate. So if we use lightweight aggregate, it will significantly reduce the total concrete weight. So lightweight aggregate made with lightweight aggregate, cellular concrete, voids in the cement base, no fine concrete means that concrete without sand or without fine aggregate. So here is some example of the coarse aggregate, lightweight aggregate. These are artificial or man-made coarse aggregates. We replace it with the normal aggregate, and this type of aggregate that has so much voids and will be lighter than the normal aggregate used, or normal weight. You can see how much void does it have, and you can expect how light is this particle compared to the gravel or granite or any other, the most common use. So these lightweight aggregate will significantly reduce the weight of the concrete. But at the same time, since we have so much voids and the existence of voids inside the concrete itself, it will also decrease the strength of concrete. So you need to understand that yes, we can get lighter weight concrete, at the same time lower strength of concrete. So in general, let's just make it this one in general here. This is the no fine aggregate. This is one of the concrete, lightweight concrete by the method of not using sand. We use only coarse aggregate, cement and water. We don't use sand or we don't use fine aggregate. So we will also get concrete lighter. This is the third method, that we create voids in the cement paste. This is the cement paste. So we create voids in the cement paste. We call it sealer concrete. And the existence of voids can reduce the concrete total density. So there is a characteristics that reflects the lightweight concrete in general. The lightweight concrete is produced as a result of creating voids inside. And since we have a high voids inside the concrete, then it will be a good isolation properties. Isolation from the heat, isolation from the sound, so it has a good sound and good thermal isolation. It will have a high water absorption because there is so much voids inside the concrete, and the water will be easily go and fill all these voids and penetrate inside the concrete, so the water absorption will be higher compared to the normal weight concrete. Shrinkage also will have a significant shrinkage. That this is a problem that could also happen to the concrete that has lightweight properties. So what are the advantages and disadvantages of this kind of concrete? It reduces the dead load, of course, because it's light. Reduce the size of foundation because the dead load is decreased, and when you do the design for any structures, you calculate the load coming from the load of the columns, the load of the concrete, the weight of the concrete, and you can consider it as a dead load, and it can be being carried from the foundation. And since the high load coming is the big size of foundation that you need to consider. And since we reduce the dead load, so we reduce the size of the foundation. Formwork experience lower with low density, better thermal and sound isolation also. It's also good, has a good workability properties. The disadvantages, it also has a high water absorption, which is not good for the concrete because it's allow the water to go and penetrate and could reach to the steel bars and failure will start. Need to use higher cement contents, which means that you put extra cost. Lightweight concrete are porous and show poor resistance to the durability, so low durable concrete, and also normally it will have lower compressive strength. Where do we use this type of concrete? We use it for as a partial or thermal isolation. If I need some application where I need to isolate the heat, isolate also the sound. So lightweight concretes, which has so much voice inside, has a good isolation properties. Component built for high-rise structure and reduce the dead load. Yes, bricks, roofing, tiles, also another application where do we use this type of concrete.